So in this lecture, I want to go through electron withdrawing groups. And what I like to how I want to frame this um, is making the best of a bad situation. And that's really, to be fair, that's an EAS, or electrophilic aromatic substitution reaction. So in electrophilic aromatic substitution reactions, they make the best of a bad situation. So we've already touched on how these work by inductive effects. So if we say through inductive effects, I want you to think about differences in electronegativity, where we have more electronegative elements bonded to our benzene. So we have more electronegative elements bonded to our benzene. That causes if we have some sort of group G, that causes a dipole to form where electrons are withdrawn, or electron density, to be more precise, is withdrawn due to polarization of sigma bonds. And polarization of sigma bonds just means it's bonded to something that's more electronegative. So that's a bit of review, maybe from a different angle, of things that we've talked about in previous lectures. What I want to do now is go into what this looks like by resonance. So excuse me, I need to make a new page. Sorry about that. So electron withdrawing groups by resonance sort of take a different approach. It's through resonance structures again. So these are a little bit easier to work with. So we can use resonance structures to understand or see how the electrons are withdrawn. Now, not the most potent of electron withdrawing groups, but definitely a potent electron withdrawing group, or an electron withdrawing group, is the carbonyl. Now, what we're going to be doing in upcoming lectures is moving into reactions of carbonyls, or carbon-oxygen double bonded systems. Now, a key resonance structure for these is one where we push the electrons up and onto the carbonyl carbon. That puts a negative charge on the oxygen, a positive charge on the carbon atom. Now, this just looks like any other pi bonded resonance structure, but it's a nice resonance structure because the oxygen is negatively charged, right? So it's the oxygen is more electronegative. So it's happier with that negative charge. Okay, so that's a pretty good resonance structure. Not as good as the original one, but it's pretty good. Now, what I want to point out here with this resonance structure is we put a positive charge right next to the aromatic ring. This is going to be how withdrawing occurs. This positive charge withdraws electron density. And again, we can do all of this. We can show all of this through resonance. So let's go ahead and try that. If we take our resonance structure of interest, what we can do is we can actually push, I should draw this as a more clear bond. We can push electrons up and onto that carbonyl carbon atom. What that will do is that will make a double bond outside of the ring. The other two double bonds stay put. And now we've introduced a positive charge at the ortho position, ortho to where that carbonyl was originally. And we can move that positive charge around, much like we move the negative charge around with an electron donating group. That is, we can move it from the ortho position to the para position just by swinging double bonds around back to the other ortho position, or excuse me, not back to, but just to the other ortho position. Oh gosh, that got ugly there. Okay. And then we can push this double bond down to remake the original resonance structure, which I'll just kind of have sweeping back here by resonance arrows. Okay, so all of these resonance structures do provide some insight into how this molecule behaves. So based on resonance, we have to think about this molecule as having positive charge character at the ortho and para positions. Now, maybe this is a delta positive, like a partially positively charged. What I just want to indicate is that the ortho and para positions have plus charge character.
I didn't get.
Have the positive charge character. Okay, so this shows a few things to us. First of all, this plus charge character indicates the benzene has less electron density, and it's this benzene has less electron density than the parent benzene. And the parent benzene, okay? Now, that suggests to us right away then that this benzene is deactivated. And how is it deactivated? It's deactivated as a nucleophile, because remember, the nucleophiles are the things that add electrons to reactions as they react with electrophiles. So if we have less electron density, we're not going to be as good of a nucleophile. We say that we are deactivated because we've lost electron density. Now, additionally, this positive charge exists on the ortho and para positions. Now, what this indicates, unlike our electron donating groups, is that reaction with an electrophile won't happen at the ortho and para position. Okay, I mean, if you just look at it this way, let's take our benzene and we'll put a carbonyl back on. If we're delta positive, at least somewhat positive, at the ortho and para positions, the electrophile that's positively charged is going to be repelled due to like charges. Okay, so those like charges are going to repel each other, and we're not going to see an electrophile react at the ortho and para positions. Okay? Now, what this means that if a reaction must occur, like if you really force it, and this is going to require more kind of assertive conditions than you would use for benzene by itself. But if a reaction must occur, a reaction will occur or takes place at the meta positions. So the reaction will take place at the meta positions, okay? Now, this is me saying, I just want to keep emphasizing, this is if a reaction has to occur. It takes a lot of work to get a reaction to occur because we have to, when this reaction occurs, we have to sort of introduce a positive charge into our intermediate complex, okay, or into the intermediate that forms along the way to give our product. Okay, so what I'm going to do is I'm going to take the electrophile and I'm going to let it react at the meta positions. The meta positions are not seemingly deactivated directly by this electron withdrawing group. But if a reaction were to occur at the meta position, we put our electrophile at that meta position, we draw the hydrogen that came along for the ride, and we put a positive charge at this position. Now, what we want to note about this positive charge is that it is not stabilized by resonance. It's just sort of a positive charge. And so what we get is we have a less stable cation intermediate than we would, a less stable cation intermediate, yeah, I'll stick with that, than we would see with benzene. Okay, but anyway, we're halfway there, so let's finish the job. The hydrogen's going to lose, or is going to fall off the molecule to reestablish aromaticity to give rise to our final product. I feel like I'm not doing a good job selling this reaction, and maybe that's because I'm doing a better job selling how poor it is. Okay, these electron withdrawing groups not only deactivate the ring, they don't provide stability the ring is nucleophile, but they don't provide stability to the intermediate complex. And so we just don't see them really serve as great substrates for these electrophilic aromatic substitution reactions. But if a reaction has to occur, I guess it has to go meta because the para and ortho positions are so destabilized. Okay. Now, if we draw other resonance structures that anyway, I'll just leave it at that. It's just not a great situation for the molecule to be in. Okay. I guess I went up a little bit. So it turns out that this is how most electron withdrawing groups behave. So most electron withdrawing groups kind of influence molecules through resonance. Okay, so let's look at some of the other electron withdrawing groups we mentioned. So we had carbonyls, and the carbonyls could be other things too. I had an aldehyde before. It could also be an ester. This other carbonyl just behaves like the one we just went over. You could show a resonance structure where you have a carbon atom that's positively charged directly attached to our aromatic ring. That is just a recipe for an electron withdrawing group, because having that positive charge just adjacent to the ring means you're going to have resonance structures where you pull electrons out of the ring and into the substituent. That puts a positive charge inside the ring, and we've been deactivated. So this is deactivated because the electrons have been withdrawn to the substituent. And here that substituent is a carbonyl. It happens to be an ester. But this is actually how most things behave. So I know this is basically the same example, but if we look at the other electron withdrawing groups I want you to be aware of, we have the nitro group. Now the nitro group, if you draw it as its full Lewis structure, where you can actually see the bonds on the nitrogen, you recall that no matter what we do to the nitro group, the nitrogen is always positive. Okay, otherwise we draw a pretty low contributing resonance structure. So what that means is nitrogen already being positively charged, it can just right off the bat soak up electrons from the aromatic ring. Now, what does that resonance structure look like? Well, we take those electrons over, we make a carbon-nitrogen double bond. But at the same time, we have to avoid breaking an octet. So on the nitrogen, so we push the electrons up and onto the oxygens. The nitrogen both accepts and pushes away electrons, and it maintains its positive charge character. But we introduce a new positive charge in the aromatic ring. If you look, we're still overall neutral. Now we just have 2 minuses and 2 positives as opposed to 1 of each. But that positive charge shows that we are deactivated again. So the NO2 withdraws electron density through resonance. And inductive effects, because the nitrogen is more electronegative than carbon. Okay, now similarly, we could draw the exact same thing for sulfur. And the sulfur I'm speaking of is the sulfonic acid that we make by the sulfonylation of benzene. So if we take this, we draw resonance structures of it. What I would do is we could just push electrons onto the oxygen, and we could actually do it in both directions. That's a viable resonance structure because now everything has an octet as opposed to sulfur expanding its octet. And when we do that, we put a 2+ on the sulfur atom right next to the aromatic ring. So we're definitely withdrawing electron density. We don't even need to worry about inductive effects because the resonance effects are so strongly withdrawing. Turns out you really don't see electrophilic aromatic substitution reactions on things that only have, unlike benzene, sulfonic acid, and nitrobenzene. You just don't see it. So we're still positively charged on that sulfur atom. So it's the same sort of thing. So what I would want you all to be able to do is to just kind of show a few resonance structures that explain why something is an electron withdrawing group. I've sort of given you all of the answers. Okay. So that'll do it for this lecture where we looked at electron withdrawing groups. In the next lecture, we'll look at what happens when we put these things together. That is what happens if we have multiple substituents on a benzene ring. We have electron donating, electron withdrawing, 2 electron donating groups. What sort of happens? Okay, so we'll finish with this one now.